Okay, hi everyone. So let's go through some exit pass on integration techniques over here. So we have four sets of things to consider, right? I think in A levels we need to start to consider a little bit more about the complexity of our integration lah. So that's why it will be very important that you think of all these techniques, right, and revise them accordingly. Right, so let's take a look at our set 1, right? Set 1, we have two items over here, and both of these items over here, right, if you look at the integrand, both of them are actually products, right? So for products, right, of course it will be very tempting to jump straight to integration by parts, right? Because usually we use integration by parts to integrate our products, okay? So lo and behold for A, right, okay, um, yeah, for A, right, it will be definitely integration by parts. So how do we do integration by parts again? We need to consider we need to consider the order in which we choose our U and dv. So over here we have our LIATE, right? So logarithmic inverse trigo function, what do you call this? Algebraic trigo and even exponential function. Okay, so this one on the left we choose the one that is more on the left we choose as u, the one on the right we choose as dv dx. Okay, so this liate thing over here, right? So over here let's choose, right? So our u would be the one in front. So actually if you compare a, the algebraic and the exponential, right, the algebraic come first, so that's why we choose u to be x, right? And then we choose dv dx to become e to the power of 3x. So to be honest, the whole principle is which one can you differentiate, which one can you integrate lah, or which one differentiate, right, will vanish, or which one integrate will vanish, that kind of thing, right? So for this case, right, our du dx, when you differentiate, the x will vanish and become 1. dv dx, when we integrate, we will have 1/3 e to the power of 3x, like this. So let's put everything together using the formula for the integration by parts. Now, of course, in the lecture notes, there's going to be a format, right? And the actual formula for integration by parts. Now, a shorthand in which we can use is actually when this is presented in a u dv, right? Okay, right, u and dv dx, right? So what we can do is we can integrate to ultraviolet, integrate voodoo. Okay, so ultraviolet voodoo is our acronym. Okay, so or any acronym that you like to use. Okay, so let's take a look at our uv, so u and v. So we will have, okay, for the next step we will have um x times 1/3 of 3x, so x times 1/3 of e to the power of 3x, okay, minus v du, right, minus v and du dx, so minus 1/3 of e to the power of 3x times 1 dx, right? So lo and behold, we have 1/3 x power e power 3x. Okay, then this 1/3 over here, how do you integrate e to the power of 3x? You need to, is e power 3x, and we need to divide by 3 because of the reverse chain rule. So we have something like this at the end of the day. Okay, so this is for the part A for set 1. Now part B over here, right, when you look at this, right, now very tempting to also think of integration by parts. Okay, so let me write this technique over here, hold on. Right, so this is the technique for part A. Now let's take a look at the technique for part B, right? Over here, right, you may think that, hey, actually it is integration by parts, right? Actually it is not there, because, right, you need to observe something. You need to observe this and this over here, right? This one, right, you try to differentiate this. Can you get something like an x, right? In fact, actually you can, because, right, if you were to treat fx to be equals to 3 to the power of x squared, when you differentiate to become f prime, it will become 6x, right? So you actually have an x over here, and what is missing is that 6, right? What is missing over there, right, is that 6. So the thing is that this one, right, the integration technique is actually your reverse chain rule. Okay, reverse chain rule, or so-called your so-called f and f prime. Okay, f and f prime of x. Okay, now so let's try to see what this is. This one we need a 6x, right? So I need to balance a 1 over 6 in front, right? And this one, right, is in the format of this. Okay, where it is f prime x e to the power of fx, right? So essentially, right, what are we integrating, right? So this one is our standard function, the e, right? So when we want to integrate e, we will get back e to the power of fx. And the part in front, right, the chain in front over here would be disappear. Because when you differentiate this and come back over here, right? When you differentiate, right? Because of chain rule, you have e to power fx times f prime x, right? When you differentiate. But when you integrate, right, this f prime x will be missing. So it will be reabsorbed back into the original function. Okay? So now, right, the thing is that in order to queue or to engage your reverse chain rule, you need to make sure that there is an fx and f prime x. Okay, so more often than not, right, before you jump into integration by parts, right, you should observe if is there an x or f prime x for all your integral. Okay, so in lo and behold, actually you can find your fx and f prime x over here. Okay, so now the thing is we will integrate to 1 over 6. Now integrating this is actually integrating the e. So at the end of the day, it's just back to e with the original function. Okay, e to the power of 3x squared plus c. Okay, so this is the answer for the integration in set 1. So first one being integration by parts and reverse chain rule. So once again, you need to observe whether is it integration by part or reverse chain rule. Okay. Okay, so now let's take a look at set number 2. Okay, now for set number 2, right, the first one over here, right, is to integrate sine x and cosine x. Now also at the first glance, right, you can think whether is it integration by parts or not. Actually can lah, it's debatable, right? You can think of it as integration by parts. You can also think of it as an f prime thingy, where this is fx to the power of 1. Also can think of like that. Okay, now because this is f prime, or the other way around, doesn't really matter, right? Now so you have many methods that you can do. Okay, now however, right, the third method that I want to say, which is the more classy and the more like the actual method lah, right, that we should be thinking of, is actually to use the double angle formula, right? Because if you recall, okay, if you recall, sine 2x is equals to 2 sine x cos x, right? And because of that, let us try to form this into our double angle, right? So this one over here, we can rewrite this as half of sine 2x. And sine 2x is something that we've integrated before in our secondary school additional maths. So over here, what do we see? This one is just negative half of cosine 2x over 2. Or actually the negative inside because we are, yeah, okay, straightly speaking, the negative is inside, plus c. So altogether, this one over here would be negative 1 over 4 cosine 2x plus c. Okay, so this one is the easiest or the best method to do for this, right? To recognize that it is part of your double angle formula. Okay, now so for part B over here, now you observe, right, now we have a sine x and cosine square x, right? So it is very tempting, right, to also to think of integration by parts because it's a product, or you can even, it's tempting also to use our trigo formula on this one, right? But what I want you to see is I want you to recognize the structure over here. Okay, so if I were to put like this, sine x, right, and wrap this into bracket like this, right? Now, can you see that this one over here, right, the technique over here is actually your reverse chain rule. Okay, why? Because if you observe, fx is cosine of x. Then when you differentiate f prime x, you get negative sine x. Okay, so what is it wrapped in, right? So what is the structure of this thing? So this one over here, right, is in this structure. Okay, this one over here is in this structure, a power rule kind of integration. Okay, so the thing is, if you integrate a power rule, how does it look like? In general, power plus 1 over the new power plus c. So what do you integrate? Over here it is fx. What happened to the chain? The chain is already divided and gone in some sense. Okay, so for this one over here, if you compare, right, look at the structure. The structure is E. For this question, the structure over here is a power function. Okay, so because of that, right, because of that, now we also need to balance with a negative in front and behind. Okay, and because of that, our thing would be power plus 1 over the new power plus c. Okay, so this would be part B. Okay, the integration technique for part B. Okay, so now moving on to part C. Part C over here is 1 over sine x cosine x. Like what we mentioned just now, that sine x cosine x, it will be suitable to think of our double angle formula, right? So we can change this with our double angle formula to look something like this. Half sine 2x dx, right? Now 1 over half, keep change flip, you get your 2. 1 over sine, this is actually cosecant of 2x dx, right? So how do we integrate cosecant over here? The integration technique is actually to refer to MF27 because this is a new integral this year. Okay, so over here, right, if you notice, you can actually get your negative ln modulus cosecant 2x plus cotangent 2x. Okay, this one over here, right? And because of the reverse chain rule, right? When you differentiate this, after the ln and the cosecant and so on, we still need to differentiate you still need to multiply by 2. So in fact, at the back, right, we need to multiply by half. Okay, we need to divide by 2 because this one over here is our reverse chain rule. Okay, likewise, right, last time when we learned how to differentiate this, right, this one over here is negative cos 2x divided by 2. Why we divide by 2 is actually reverse chain rule. When we differentiate, we times 2. When we differentiate, we divide by 2. Okay, so yeah, so this is our reverse chain rule. Okay, so then let's tidy up everything. So the 2 and the half will cancel. Then I will get something like this over here. Okay, so this will be the final answer for part C. Okay, so moving on to part D. Part D over here, we have sine x and cosine 2x, right? Now, so the thing that we need to take note over here is that this is x, this one over here is 2x. So as much as possible, we should try to make them the same, right? Observe over here that we can't get it to ff prime. Sure, we can think about the integration by part, but it's actually unnecessarily, what do you call this, complicated. Okay, so the thing is to make the x and the 2x the same first. Make it the same layer first, right? So a good way for us to do is to change cosine 2x to the double angle formula to 2 cosine square x minus 1. Okay, up to you. If you want to choose the other one or the other version, up to you. But maybe it's more suitable to do this because when you see this, we got sine x. Okay, we have our 2 sine x cosine square x. Okay, and this one, right, is something that we've done in the earlier part of the video. Okay, so altogether, this one over here will be negative 2 over 3 cosine cube x, which is what we've done earlier lah, right? Bring the power up. Okay, so this one is the ff prime, power up. Then so that's why you power go up, you divide by the new power. Minus sign integrate will become plus cosine. Okay, then plus c. Okay, so the idea over here is, right, to make the angle inside the function the same. Okay, so that's over here for part D. Okay, now for part E over here, now let's take a look, sine cube x dx. Now likewise, right, for sine square x dx, how do we integrate this one? This one over here will make use of our double angle formula, right? And the double angle formula that we are considering is, okay, this one over here, double angle formula, right? Cosine 2x equals to 1 minus 2 sine square x. So making sine square x the, what do you call this, the subject. Over here I will get half, right? 1 minus cosine 2x dx. And because of this, I can integrate this to x plus sine 2x, or still minus. Okay, sine 2x over 2 plus c. Okay, then we can multiply the half in. Now, likewise, for our sine 3x, okay, sine 3x, right, because we can't integrate this directly, this is not a linear function with a power, right? The power function, right, only works for algebraic version. Otherwise, we need a reverse chain rule, like how we see in part B. Okay, so because of this, right, for sine cube x, right, what we'll do is I'm going to split this to sine x and sine square x. Okay, I will split this to sine x and sine square x, and then, okay, what I'll do next is I will change this into 1 minus cos square x dx. Okay, and because of this, I will see that I will need to integrate sine x minus sine x cosine square x dx. Okay, so integrating sine x would be negative cosine x. Now integrating this one, right, is something that we integrated earlier actually, right? So because we've broken down to this, we can actually use the ff prime to deal with this. So this one over here will be plus minus 1 over 3 cosine cube x. Okay, so this one over here, once again, this one over here is a power function where we power up and we divide by the new power. Okay, so it's the same thing over here. At the end of the day, plus c. Okay, last but not least, for part F. Now, part F is a little bit special because f, right, over here is an inverse function. Okay, and for inverse function, right, this is what we learn integration by parts for. Okay, so once again, we learn how to do integration by parts, right, so that we can deal with ln x and sine inverse of x, right? So the idea when we expose us into the chapter, right, is when we have the reverse chain rule. Okay, this unlocks our ability to integrate tangent x and to integrate cotangent x dx. Okay, and when we unlock integration by part, right, it unlocks our ability to integrate ln. It unlocks our ability to integrate inverse functions like this. Okay, so this one over here is the purpose of why we learn these two skills in this chapter. Okay, part of the reason why we learn these two skills in this chapter. Okay, now so because of this, right, okay, let's try integration by parts. So let's set this up over here. So there's an invisible one. Okay, so let's set this up. So LIATE, right? So obviously, which one can differentiate? Which one suitable to differentiate? Which one suitable to integrate? So obviously, right, the U would be our sine inverse of x because we can't even integrate the sine inverse. And then our dv dx over here would become 1. Now, so this one we differentiate using your MF27, or if you know the result, 1 minus x squared. Now, then this one over here, the v integrate to become x. So now let's call out our this one, u dv is ultraviolet voodoo. Okay, v du. So because of this, right, now what is u and v together? This one over here is x sine inverse x. Okay, minus the voodoo part over here. So this one over here will become x over 1 minus x squared dx. Now let's take a look at what is this and this. Do we have an f and f prime? Actually we do, because if you check, if fx is equals to 1 minus x squared, f prime x over here is negative 2x. The one missing, right, is your 2 inside and your half on the outside. Okay, then the next thing is, what is the structure of this integration? Now, what is the main thing that we're integrating? We're actually integrating the square root. So in fact, this one over here, right, is this kind of function where the fx is inside the power function, and for this case this is power half. So because of that, right, we have x sine inverse x minus half, right? Then over here, right, power negative half plus 1, okay, divided by new power plus c. Okay, so this one over here is power plus 1 over the new power plus c. Okay, and because of this, these two will cancel each other out, and then we'll get something like this. Okay, so that's for set number B. And in set B, let's take note of the various ways to integrate again, right? We have our double angle formula. Let's take note of reverse chain rule, right? Let's also take note of the identities, right? And ideally, right, for powers, we rely on our reverse chain rule. Okay, now moving on to set number 3. Okay, so I would argue that this one would be one of the more tedious kind of integration, because fractions, right, is a bit tedious, and that in A level, right, the denominator has a quadratic component over here. Okay, so yeah, so let's take a look at one by one. Okay, so the thing is, when we have a quadratic as the denominator, what I would tend to do is I will try to do two different things, right? So the standard technique number one, the technique number one is to split this and factorize this, and we do partial fraction. Okay, then the second method over here, right, is to do completing the square. Okay, and after completing the square, right, we make use of our MF27, and for partial fraction, most likely we'll use ln. Okay, and here in this one, I will show, in your lecture you should know that it's already equivalent, so here very quickly I'll also show you the same thing, right? So let's look at method 1, partial fraction, right? And I think it will be easier if we were to make the denominator positive. Okay, now then in the next step, let's factorize our denominator. Okay, now once we factorize already, let's start to invoke our partial fractions and break this out to two separate fractions. Okay, so this is something that we've done in additional maths already. So I'm going to let negative 2 over the fraction that I have, right, to be equals to the sum of two different fractions. So when I cross multiply, right, very quick cos, when I cross multiply, this is what I get, and I'm supposed to sub in values that will make these brackets 0. Okay, so the first thing that I'll do is when x is equals to 5, so on the left hand side is -2, on the right hand side will be 6a, so a will be equals to -1/3. Okay, then when x makes the other bracket 0, when x equals -1, on the left hand side is -2, on the right hand side is -6b. So b over here would be a positive 1/3. And so because of that, right, I can change the fraction to look something like this. Okay, so now is to break the big fraction into two smaller fractions. Then let me bring out 1/3, right? And now we can integrate this to have negative ln of. Now for this one, let's remember to modulus. Okay, modulus over here. Okay, then right, if you notice, this one over here has negative power, so we can actually bring the negative power up to make it power -1, right? And we will see that we have something like this, x plus 1 divided by x minus 5. Okay, so this one over here plus c. So this would be our final form of the integration for part A. Alright, so this one is to use method 1 to do partial fraction. Now let us compare. Again, with the same question, let us compare how do we complete the square and do it. Okay, so starting off like this, right? So I'm going to aim to complete the square for the denominator over here. So if you follow your A math in your secondary school, it will look something like this. Okay, so it will look something like this. Okay, so now we should complete the square, and we update the denominator with this. So 9 minus x minus 2 square. Okay, so if you take note over here, right, we can make use our MF27, right, the formula in MF27 for a quadratic, and it is actually a square minus x square. Okay, okay, so at this point, right, you may wonder why, right, even though you get this and this, right, you may wonder, right, how come at the end of the day, both are like you have the weird denominator over here, right? But you need to take note that, right, both the denominators over here, right, this one over here is for the one below, I can do something like this, right? And then I can do something like this. And because of the modulus, right, whatever that is negative would still be like this. Okay, so something for us to take note that because of the modulus, right, we can actually do something like this. Okay, and so because of this is why both the expressions are equivalent because of the modulus. Okay, so when you see that your answer is not really like the answer given in the answer sheet, then then don't worry, because actually should be equivalent. Okay, it should be an equivalent one. Okay, so next let's move on to part number B. Okay, now so before jumping right into the integration technique, right, or looking into the MF27, you always have to constantly ask yourself first, is this f and f prime? Alright, or the other way around, is there an f and f prime in this question? Actually, yes. So because of that, the technique involved in doing this would be our reverse chain rule. Right? So what we are missing over here, right, is a 4 and a 2. Right? Over here is just 2 and a 1. So what I need to do is I need to top up a 2 into the numerator, so it will look something like this. Okay, and then the denominator stays the same, right, in order to match the f and f prime. Now let's take a look at this structure over here. What are we integrating? Okay, so this one over here is an f prime over f, right? So if you think about it, right, we are actually integrating this structure over here. So how do we integrate this structure? This one over here, right, will give us ln. Okay, ln of the function. Okay, so this is the integration technique that we will be using. So this one will be half ln of the function modulus. Okay, so that's it for part B. Now moving on to part C. Okay, so first, right, we need to ask ourselves, right, when we differentiate here, will we get something like this? So let's check lor, right? So let's check. Over here, right, if fx is equals to 3 minus 2x minus x squared, so when we differentiate, we should be getting something like this. Okay, however, this one is a positive 2x minus 3, but we after some juggling, right, we can actually do something like this. Okay, so it's either you juggle, right, you add a positive negative with you, or you proceed to do the mapping method or the equivalence method, right? So you want this to be expressed into this, right? So I will let this, the 2x minus 3, right, I want to express this into this form so that I can do the reverse chain rule, right? This one over here, and another difference would be a constant on the outside. Okay, so how should we go about this? So what you can do is you can compare coefficients, right? So comparing x term, okay, so 2 on the left hand side will become negative 2a on the right hand side, 2ax. So a would be equals to negative 1. Okay, then no choice, we want to compare constants. Okay, so on the left hand side is negative 3, on the right hand side is actually negative 2a plus b, which is equals to negative 2 minus 1 plus b, which is 2. So b over here would be negative 4. Okay, sorry, should be negative 5. Okay, now so because of this, right, now so I'm going to write it in this form over here. So this one would be a negative 1 of minus 2 minus 2x. Okay, so minus on the outside of the whole fraction. Okay, now for the second fraction, right, I need to minus, hold on. Okay, I need to minus 5 of this one as well. Okay, so the first one over here, right, is going to be an f and f prime. Okay, and the structure, right, even though this is 1 over, right, what is this power over here for this square root? Actually, the power is negative half. So the structure that I'm seeing over here, right, is actually something like this. Okay, it's actually to the power of negative half. Right? So because of that, right, when you integrate, right, negative half power plus 1 over the new power, the chain will disappear. Then over here is plus c. Okay, so because of that, right, so let us integrate this now. Okay, so we are going to get something like a negative of the thing. Okay, so this is for the first one. Now for the second one over here, right, if you take a look, right, this one over here is a quadratic nested in a square root. If you refer to MF27, and then that is a constant on top lah. Okay, so the main function to integrate is this. If you observe the MF27, right, actually this one is in a completed square form. So before that, right, let us do the completing the square for this one, which will look something like this. Okay, then we use the following MF27. Okay, and we can express the second fraction, okay, in as, okay, something like this. Okay, so let's fix the first one. So the first one, you will see it nested nicely in a square root. Now for the second one over here, right, would be applying the MF27. So I will get the x over here over a. 4 is a square, so a is 2. Okay, so our integration would be looking something like this for part C. Okay, for part D over here, let's observe that actually this one the degree is 2, this one the degree is also 2, so it is something like an improper fraction. And for improper fraction, right, what do we do first? We will need to do the long division first. Okay, so we got one whole part and minus 4x as the remainder. So we have one whole part minus 4x over this one right over here at the remainder. Okay, so now at this step, right, let's ask again ourselves, is this an f and f prime over here? Okay, so the answer is actually yes, because if you notice, if fx is equals to this, right, when we differentiate this, we will should get 2x plus 1. Over here with 4x, right, actually when we add in, we can actually balance back lah, okay, what we need. Okay, so how do we integrate this over here? Okay, so we not say integrate, how do I express this and break up into what I want, which is actually to follow this thing over here. Okay, so I will need to let, okay, I will need to let okay, this one 4x. Okay, I think maybe let's put a minus 4x then. Okay, easier, to be equals to a times of what we want plus b. Okay, okay, so because of this, right, let me rewrite the fraction into these two fractions. Okay, now we will also try to what do you call this, let me also try to complete the square for this so that we can roughly see what's going on at this step. Okay, and because of this, let me update the denominator to the completed square form. Alright, so and then take note over here that this one, right, a square is equals to 3 over 4. So a, right, the positive root would be actually root 3 over 2, in which we'll be using a bit later. Okay, so now let's try to integrate then. Integrating 1 will give us x, right? Then this one over here, right, now you need to ask yourself, what is this form over here? This is f prime over f, right? And the power over here is actually 1, right? Power negative 1. How to integrate power negative 1? It will become ln. So minus 2 ln of this. Okay, so these are some things that you need to think about on your own, right? Your inner voice. Now, then, how do we integrate that one? This one over here, we can refer to our formula list, alright? And then we can actually apply this to 2 over, okay, 2a. So the a is this one. Okay, this is the a, right? Ln of, now in the numerator, okay, so this one is x, so called our x minus the a, okay, and then we also have the x right, at the denominator plus the a, like this. Okay, now what we are going to do, right, numerator and denominator we times 2 to actually make the 4-layer cake become just 2 layers, right? We try to have maximum 2 layers only, okay, in the cake. So, right, what we have over here would be 2 over root 3 ln of 2x plus 1 minus root 3 divided by 2x plus 1 plus root 3 plus c. And there we have it. This is how we integrate part D. Okay, super tedious, but this would be the end of the whole series lah for fractions, algebraic fractions. Okay, so hopefully you managed to sit through the whole thing and roughly take a look. Okay, take a look at the whole series. Okay, usually is partial fraction complete the square, right? Right. Likewise, you also need to complete the square, especially for square roots, and also at the same time check whether you have an f and f prime or not. So usually the first thing to ask, right, is to ask whether is it of this form, okay, or whether is it of this form, is it the power form. Okay, so yeah, is okay. So this is for set C. So moving on to the last set, which is very interesting, right? So let's start off, which is a series of ln. Okay, I think you can see this in other examples, right? But for this one, right, I want to follow specifically for ln. Now how do we integrate ln, right? The reason why we learn integration by parts is to tackle this problem. Okay, so this one, right, the technique over here is integration by parts, and what is missing over here is actually the 1. Okay, so what are we going to do is I will need a LIATE, right? This one over here is U to differentiate, this one over here is dV to integrate. So obviously U would be my ln x. When I differentiate U, right, I have a very friendly 1 over x over here. Then dV dx is 1. Then V after integrating is x. Very nice. So making use of the right ultraviolet would do. Okay, so we have the UV, right? So x ln x. Then would do over here be minus okay, right? So this is actually just 1, right? So how do I integrate 1? So simply that's just x, and that's it. Okay, and that's about it. Okay, now I think we can drop the modulus because the domain, right, should be also positive. Alright, for this one. Now let's take a look at part B. Part B over here, right, is actually ln x over x dx. Now, so quotient rule or something a bit weird, right? Let's also ask, is there an f prime going on over here? Let's try to find the structure, right, of the f prime, right? And indeed, we actually have the structure, and it looks something like this. Okay, so obviously you can see, right, fx is ln x, f prime x is 1 over x. So this one over here is our reverse chain technique, right? Now, but the thing is, what form does it take? Right over here, what form does it take? Okay, so over here, right, if you notice, right, it's actually pretty invisible. It actually takes up this form, right? Power n, then divided by power n plus. So you raise the power, and you divide by the new power. Okay, so over here, right, there is an invisible power 1. So when you do the reverse chain rule, it's actually ln x whole thing square over 2 plus c. Okay, so this one over here, take note and be careful. Okay, part C. Part C, this one is x ln x. Now this one, very obviously, this is integration by parts because you can't really see the the f prime over here. Okay, right? So integration by part, same thing, u and dv dx. So the one to differentiate is ln x. Okay, easier after we differentiate. The one where we want to integrate, easier after we integrate, is x. Okay, then ultraviolet would do, so half x square ln x. Okay, minus v du, so half, okay, x square over 2, 1 over x dx. So let's tidy this up over here. Okay, then last step would be to get something like this, x square, then divide by 2 plus c. Okay, so this one over here for part C. Okay, last but not least for part D. Okay, so this one 1 over x ln x dx. Okay, so this one over here, right, is a bit tricky, but you need to realize that you can write it in this form like this. Okay, and in this form, right, you need to realize that actually this is fx, right? When you integrate ln x, you get 1 over x. So what is the structure of this one over here? I think you can start to see that actually this is f prime over fx. So how do you integrate this over here? So this one would be ln of fx, the original function, okay, plus c. And because of this one over here will give us ln of ln x plus c. Okay, so this ends the video on the integration technique speed run. Hopefully it is worth your time, and hopefully now you get a better understanding of what to do, and now because of this you have a good idea and you can start well and then you can finish strong and finish fast. Okay, so hope this helps, and all the best.